So the question that I returned to was, what if Earth's surface was smooth? It's from episode 63. It's actually one of our later episodes, but I thought it's fitting for our throwback question just because this was, especially my answer to this question was like one of the bigger mistakes that we've made on the show, or that I've made on the show. So just to kind of summarize the question or my answer that I did for this question. So I covered like rain and water and...
No, I covered rain and water just now, Chris.
Yeah, I know.
You guys stealing my answers, I think. Or we're just becoming a hive mind because I somehow did something that's in Ben's answer and in your answer.
It's actually kind of a good thing that I went after you, I think. You'll see why. But yes, I mainly looked at rain and water and like runoff, how runoff works, because if the Earth is smooth, then you don't necessarily have runoff. And then I ended up looking at like impermeable surfaces, specifically granite, and I looked at if there was like a really big area of granite that was completely smooth and it's impermeable, what happens to the rain when it falls onto the granite. And my endpoint for that was that all the water drops would group up and form into one giant drop, and you'd have like a wall of water in front of you. That's wrong.
Yeah.
I think it was actually pretty immediately after that I realized it was wrong, but I never had a chance to talk. I think we did talk about it in one of the behind the scenes.
Yeah, we talked about behind the scenes, and I think that, and unless you're about to just get into it, but I think it was a scaling problem of surface tension.
Yeah. So I actually based that theory off of the property of contact angle. So like contact angle is like the interaction between the liquid and the solid. So like it depends on what materials you have, but like for water on granite, it has a very specific contact angle where like the edge of the drop is at a certain angle. And that's supposed to be maintained no matter how big the drop is. And that's based on another property called wettability for the granite. And that's all constant because it's all the same material. So that is still true. The contact angle remains the same, but I scaled it up incorrectly. So it won't be a giant drop. What will actually happen is the gravity will actually overcome the surface tension part of the drop, and it'll flatten it out, and you'll have basically just a shallow puddle, and then the edges of the puddle will have that contact angle maintained. So that's what will actually happen. That's boring though, and I wanted to try to make this giant water drop thing work. Didn't necessarily want to correct my fact. I wanted to force my fact to be correct.
I found the fun thing, so I'm just going to change the question until it suits me.
Yeah. So what can I do to achieve this? First, I looked into what actually causes the drop to flatten out. So it is gravity. And there's a property of a water drop that's called capillary length, which is basically the relationship between surface tension and gravity. So a drop with a radius smaller than the capillary length is considered a microdrop, which means that surface tension, the shape of the drop is governed by the surface tension, and it becomes like a dome shape. If the radius of the drop is larger than the capillary length, then it's considered a macrodrop. And that means that the gravity will dominate the surface tension and it'll flatten it out. It won't be a dome shape.
Macro drop is a really good DJ name.
True. So the capillary length of water is 2.7 millimeters. So that's the biggest size dome drop that you can have. It's 2.7 millimeters. You're not going to get a giant drop. So I'm like, okay, I need to increase the capillary length of water in order to get my giant drop. What are the factors that affect capillary length? There are two. I mean, obviously there's gravity and surface tension. So obviously one way I can increase the capillary length is to reduce the gravity. So, I mean, we've done that on the show before. We've reduced gravity. If we have reduced gravity, we can have a giant drop. Or if we like put it on a different planet or something, if we put it on the moon, we can have a bigger drop. But that's not really what this question is. This question is, what if the Earth was smooth, which means that our giant drop has to be on Earth with Earth's gravity. So we can't change gravity, which means that we have to change surface tension. So what exactly is surface tension? So what causes surface tension is, it's basically depends on two things, cohesion and adhesion. So if you're looking at water, or like inside a drop, each water molecule is surrounded by a bunch of other water molecules, and they're all attracted to each other. And that's cohesion because it's like the same material molecule is attracted to another of the same material. That's cohesion.
God, my brain is like really, really waiting for like the high school teacher mnemonic device to tell me the difference between adhesion and cohesion.
Well, the difference is basically just adhesion is between two dissimilar materials, whereas cohesion is two similar materials. So cohesion is happening inside the water drop, and it's all equal in all directions, so it nets zero. But at the surface of the drop, it doesn't net zero because you have the air, and the interaction between the water molecule and the air is adhesion. And the strength of cohesion is stronger than the strength of adhesion. So you have a net inward force towards the center of the drop, which is kind of holding the drop together. And then you also have a tension force that's parallel to the surface of the drop due to the cohesion between the molecules next to it. So surface tension is kind of a combination of those two forces, the inward force and the tension force. And that's what surface tension is. So the surface tension of water specifically is 72.8 millinewtons per meter at 20 degrees Celsius. And that's actually like one of the water has one of the higher surface tensions of all liquids. It's not the highest, but it's up there. And there's a reason for that. So a water molecule is H2O, so there's two hydrogen molecules or hydrogen atoms and one oxygen atom. And because of that, it can form 4 hydrogen bonds between 4 separate water molecules next to it. So the 2 hydrogen atoms form a hydrogen bond with 2 separate oxygen atoms of different water molecules. And then the oxygen atom forms 2 hydrogen bonds between 2 other water molecules. It's a lot easier to explain if I had like a diagram, but I don't.
Yeah, they kind of just like stack on top of each other, where like the O goes between 2 other H's from 2 other ones, and then on top of that is another 2 H's. Like kind of alternates between 2 H's and an O.
Yeah.
But also in probably a 3D complicated lattice that is much harder to explain on a podcast.
Right, yeah. But basically the end result is just it has 4 hydrogen bonds, and hydrogen bonds are actually pretty strong. And that's why it has a pretty high surface tension. So I'm like, okay, so surface tension is due to this chemical bond between the hydrogen atom and the oxygen atom, which means that we need to increase that somehow. So I looked into what the relationship between the strength of a chemical bond is. And the strength of a chemical bond is expressed in Coulomb's law. So it expresses electrostatic force as a relationship between the charge of 2 ions and the distance between those 2 ions. So if we want to increase the strength of the chemical bond, that means we have to change one of these things. But if we change the charge of the ions or like the distance between them, that means we're changing the atoms, or we're changing the molecules, which means that it's not really necessarily a water molecule anymore. And I want to make a giant water drop, so it needs to be water. But another thing that's in this Coulomb's law is a thing called Coulomb's constant. So it's just a constant that people use when they're talking about like electricity and stuff. And Coulomb's constant is 8.988 times 10 to the 9 Newton meters squared per Coulomb squared. And it's just a constant that you multiply the charge of the ions in the distance by to get the number.
My mental image of you right now is just like surrounded by science textbooks of different subjects being like, and then Coulomb's law, and like flipping over the next book is over here.
I mean, that's basically what my research was. I was like kept on going deeper and deeper and deeper until I got to where I wanted to get to.
I'm absolutely here for it.
I think in order to achieve our giant water drop, this is what we're going to change. We're going to change the Coulomb constant just arbitrarily. I guess basically my hypothetical is what if Coulomb's constant increased? And that will get our giant water drop. So I defined our giant water drop as, I kind of had to pick a size. I just chose to make it person-sized because that seems like a decent benchmark, I guess. Which means that the capillary length of our drop would have to be 6 feet. And that means that we need our surface tension to be 32,671 newtons per meter. That's compared to our 72.8 millinewtons per meter. So that means our new surface tension is 448,000 times stronger than normal. Now, the relationship between surface tension and the Coulomb constant is linear. So that means that our new Coulomb constant will also be 448,000 times larger.
I'm sure that won't cause any problems anywhere else.
Yeah. So now that means that we can achieve our giant water drop now. But this also, obviously, this is like for all chemical bonds, so it applies to other stuff too.
Does it just make all chemicals unbreakable? Like,
well, I didn't really focus on everything. I focused more on like where this water drop originated from, which was raindrops, which you already covered raindrops a little bit. But the fact that our Coulomb constant is bigger now and that our surface tension is bigger, it means that our raindrops will also be bigger. So I guess I fixed your problem.
Yeah, you got me to bigger raindrops, definitely.
The thing is, there's also a linear relationship between the Coulomb constant and the strength of electric fields, which makes sense because like the chemical bond is based on electrical interactions. But that means that electrical fields will also get 448,000 times stronger. So since we're talking about rain, I want to see if this affects lightning.
Oh, pop up the next textbook.
Yeah. So I looked at what causes lightning, and I think we've covered this on the show before, but I'll just briefly go over again. So what causes lightning is there's ice and hail particles that collide with each other in a storm cloud, and this causes the cloud to be positively charged on the top of the cloud and negatively charged on the bottom of the cloud, and this creates an electric field within the cloud. Now, on Earth's surface, below the cloud, it becomes positively charged, and then in between the Earth's surface and the cloud, the atmosphere acts as an insulator between the two. And then a charge builds up in the cloud until eventually the charge overcomes the insulating effects of the atmosphere, and lightning strikes, hits the Earth's surface, and temporarily equalizes the difference in charges. So that's what causes lightning. Now, with our stronger electric fields, I don't think we're necessarily going to have more powerful lightning, because when lightning strikes, it's because it's overcoming the insulating effects of the atmosphere, and the atmosphere still has the same insulating effects. But what will happen is that the charge of the clouds it'll charge more quickly, which I guess results in more lightning strikes happening more often. So we're going to have a lot more lightning strikes. We're going to have 448,000 times more lightning strikes, which is a lot. So right now we have 240,000 lightning strikes per year around the world. With our new Coulomb constant, we're going to have 100 billion lightning strikes per year, or 3,000 lightning strikes per second.
Great.
Yeah, it's a lot. And it's not going to be spread out around the world because we don't have like a constant thunderstorm around the entire world. It's concentrated to just where there are thunderstorms. So whenever you have a lightning or like a thunderstorm or like rain or whatever, you're going to have giant raindrops, and you're going to have crazy frequent lightning all over the place. And you're just going to have these like mega storms, and that will be fun. And I'm sure a bunch of other stuff will change too, because we're changing chemistry and chemical bonds, but I focus on the storm stuff.
Yeah, I think if you increase the strength of all molecular bonds by 500,000 times, I think everything would just be one big molecule. Like, it just would be would the whole universe just be a black hole? Because it would be dense. It would be so dense, and then everything would just come together, and nothing would leave, and then it would just go into.
I don't know if it would necessarily be dense. It would be stronger, though.
Oh, I guess because it wouldn't actually.
It wouldn't bond with things it wouldn't normally
molecules
bond with.
Yeah.
It would be impossible to write out any chemicals, because you'd be like, all right, H35,612. Oh.
That was a clip from Absurd Hypotheticals, the podcast where I answer dumb hypothetical questions. For the full episode, click on the link in the description.